So the first thing uh, I want to talk about how you can find limit of a function. Suppose I have a function, so I have a function f which is, let's say, from a domain D to R. So where D is a subset of R. Okay, so I want to compute. So basically, I want to know first why I want to know what do we mean by limit. So what do you mean by limit?
क्या चीज बोल रहा हो क्या बोल रहा हो अच्छा हमने बात कुछ हुआ हो
Hello. Yeah, please
हाँ ये सीढ़ियाँ पाओ नहीं क्या
mute yourself. Hello.
ये सीढ़ियाँ पाओ ना
Abhishek, can you mute yourself? Yeah, thanks. So so I want to know what do you mean by limit x tends to a f of x is equal to L. This is what we want to know. Okay, what do you mean by this thing? Okay, what this notation represent? Okay, so before that, so to discuss limit, we need to know what is left hand limit and what is right hand limit. Okay, so to discuss about limit, we have to know what is left hand limit and what is right hand limit, right? So let's first discuss what is left hand limit. So what is left hand limit? So so I can say, so so in notation, how you represent left hand limit of a function at a point A. So this is how you represent left hand limit. Okay, so it's basically it's saying so in more or less it's saying we are taking values which are basically less than this number A. Okay, this minus sign basically represent we are taking values those are basically those are sorry which are less than this number A. Okay. So when I say that the left hand limit of a function f of x at point A is L, when I can say this. Okay, so basically what when I can say that left hand limit of a function f of x at the point A is L, when so if 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 x the if x is close to A, okay, from below, right? Below. What do you mean by this below? Suppose you have, this is your real line, this is your real line. This is your real line. Suppose this is your point A. So this one is your A. So when x is close to A from the below, okay, so when x is, so when you are taking x such that the value of x is less than A and you are going from you are going closer to A, right? You are going closer to A, then then basically f of x is close to A. Okay. So I can say that the left hand limit of the function at point A is L if the value of x when I can say that the left hand limit of the function is L. So when x is close to a, and at the same time f of x is also close to L. Okay. So in that case I can say that uh, this then in that case I can say that the left hand limit of the function is L. Is it clear? When actually, so what do you mean by left hand limit? So when actually we are taking the values from the left hand side of A and we are taking the limit, in that case we say that is basically we're talking about left hand limit. Is it clear, like what do we mean by left hand limit? Hello? Hello?
So will you take one example, please?
Yeah, no, no, no. Certainly I am going to take example, but so my first concern is whether the definition is clear.
Yes, sir.
So the thing is what basically we are doing with, so when this x is close to a, we want to see where f of x approaches, right? That is what we are doing. Okay. So so basically what actually we're so what this L is, what this L is. So we basically checking when x approaches to a from the left hand side where f of x approaches. Okay. So if I have a point L, if I have a point L where this f of x approaches, then I say that this L is basically my left hand limit, right? So when when I see that this when x approaches to a from the left hand side, I want to know where f of x approaches. Okay, if this f of x approaches to L, then I say that L is basically my left hand limit. Okay, and similarly I can talk about the right hand limit, right? Similarly I can talk about this. Certainly I'm going to give you a bunch of examples, so don't worry. So first try to understand this definition. Okay. So basically suppose, let's say I have this function, say, so this is my function. So let's say this is my uh, this graph is basically nothing but x comma f of x. So I want to compute the left hand limit of this function. Okay, so at this point a. Okay, so when actually you are coming to a from the left hand side. Okay, so suppose this is my, say this one is my a1. Okay, so at that point this is my f of a1, right? And when I'm coming to a2, then at this point this is my f of a2. Okay, so when I'm coming to a from the left hand side, if you keep taking numbers which are even more closer to a, then basically you will come closer and closer to this f of a, right? So if you take some another number, let's say here, then you will get some number which is even more closer to f of a. Again, if you take some another number which is even more closer to a, then you will get a number which is even more closer to f of a. Okay, so so in this case actually it turns out that this left hand limit for this function, this left hand limit is basically f of a. Okay, for this function, but it is not true for all the functions. Okay. I'll show you some graph in GeoAlgebra. Okay. So so the next thing is, what do you mean by right hand limit? Okay. So let's say this is I have this is L, let's say this is M. Okay, so again I'm saying this plus sign, why I'm using plus sign, because I'm coming to a from the right hand side. Okay, from the right hand side. Okay, because so see, if I'm coming to a from the right hand side, then basically I'm coming through numbers which are larger than a. Okay, so if I take a number here, this is basically larger than a. If again I will take some number here, then this is also larger than. So if I take again some few number which are even more closer to a, so still they are also larger than a. So I'm coming to a through some points which are larger than a. So that's why this plus sign is coming, and that is basically this is the right hand side of a. So that's why we are denoting this thing as right hand limit. Okay. So basically, what basically this notation tells you, what basically this notation tells you. So this basically tells you as x approaches to a from the right hand side. Side, f of x approaches to n. Okay, so if this is my f of x, so when you are coming to this so when you are coming to a, so then this value is basically your a. So this value is something let's say a, and this is basically f of. Okay. So when you are coming closer to a, this value of this function, as you can see, it's coming to n. Okay. So that is what we mean by right hand. Okay. So basically, we are checking how this function behaves from the, so when you are approaching from the left hand side and when you are approaching from the right hand side. Okay, so this right hand limit and left hand limit, they basically tells you how the value of the function behaves when you are coming to a from the left hand side and right hand side. Okay, so the definition part is clear or not?
Sir, then yes, sir, related to definition part only, can we
Huh.
say that we are calculating the value of the function at different point while we are approaching either from left or from right, right?
No, we are not calculating the value of the function. Okay, we are not calculating
Value
the
of the
value of,
expression, sir. Value of the expression.
we are actually calculating when x approaches to a, we are calculating that f of x.
Correct. That's what I'm saying,
Okay.
sir. Say for
Yeah.
example, my A is 3, right?
Yes.
So while approaching from left hand side, I am calculating at 2.9, 2.95. So I am calculating the value of
Yes.
the
Yes.
expression at
Yes.
different points
Yes.
approaching
Basically,
towards A.
yes.
Ap-
Yes. So basically, what basically you are taking when you are computing, see this, let's say a equal to 3. So what actually you are taking? You are taking bunch of numbers. Okay.
Correct.
Let's say 2.9.
Correct.
Okay.
2.95,
2.95, maybe say
9899.
2.956, let's
Correct.
say 2.966. You are taking
Correct.
bunch of numbers.
Yes, sir.
Ah.
And we are
And
calculating the
you are,
value of the expression.
yes, so basically you are going, so by taking all these numbers, you are going closer and closer to 3, right?
Right.
So then you can take some 999, then you can take 2.99999, all these numbers. What actually you are then doing, you are actually observing how these values mm,
Looks like.
looks like, or maybe you can say where this value approaches. Okay,
Correct. Where these values
this
are approaching. Right.
yes. So basically you are trying to see the pattern of these numbers. Okay, the numbers uh, which I have written in the second. Okay, so
Correct. Correct. Yes, sir. Understood. Thank you, sir.
So basically, we are checking the values of the of these things. Okay, so we are checking how these values behave. That is what we
Correct,
want
sir.
to do. So basically what I'm doing here, I'm taking all the numbers. So whatever numbers I have taken here, they are basically all are less than 3. Okay, so more or less, in this case, more or less, I'm trying to compute the left hand limit. Okay. Okay, so more or less, I'm trying to compute what is the left-hand limit, because I want to find where this f of x approaches, when this x approaches to a from the left hand side, right? Okay, so so let me uh, let me give you some. Okay, so okay, I'll show you some visuals. So before that, let me do some examples here. Okay, so so now you take, let's say, f of x is equal to 2 for all x in R, right? So this is a constant function, right?
Yes, sir. Yes.
So this is a constant function. So how this graph will look like?
A straight line, sir, parallel to x-axis.
Yes. So this is this is basically parallel to x-axis, and this passes through here 0, 2, right? Because as you can see, this f of 0 is also 2. So okay, so now what I want to do, I want to compute. So this is uh, so here x equal to 0, right? So I want to compute the left hand limit and right hand limit of the function at x equal to 0, right? So so I want to compute the left hand limit. First, let me compute the left hand limit of this function at x equal to 0. Can you tell me? Well, so can one of you tell me what will be the left hand limit of this function at 0?
2, sir.
Sorry,
2, 2.
2. Why?
It's a constant function, so whatever value of x we are putting, it will be 2 only.
Yeah. So if we'll try to go by the definition, what basically we will see. So so what basically we have to do? We have to check when x approaches to 0. So this is my 0, right? This is my origin. So
Yeah.
when x approaches to 0 from the left hand side. Okay, so when I'm coming to 0 from the left hand side, I need to check how. So I need to check where this f of x approaches, right? I need to check where this f of x approaches. So for example, if I take, let's say, this some sequence, let's say -1 by n. Okay, so if I take -1, so as you can see, the value of the function at -1 is 2. Okay, again, if I take -half, then the value of the function at -half is also 2.
Correct.
So again, if I take something -1 by 3, then the value of the function is 2. So again, if you come even more closer to 0, then you can see still the value of the function is 2. So whatever may be the value of x, whatever may be the value of x, the value of f of x is always 2, right? When you are coming from the left hand side, whatever may be the value of x, the value of f of x is always 2. So it doesn't matter how you are coming to 0. Okay, it doesn't matter how you are coming to 0 from the left hand side. So it will not change the value of f of x, right? So the value of f of x is completely independent on how you are coming to 0, right? So that's why this left hand limit of this function is basically 2, right? And what about the right hand limit? What about the right hand limit?
Also 2.
Okay, so like okay, I don't know if it is too easy for you, then yeah. So
So same thing from right hand
yeah,
side.
yeah. So the thing is, if when you are coming from to left hand side, coming to 0 from the right hand, it's the same thing happens. Okay, that's because the value of f of x is completely independent on the value of x. Like it's basically 2 throughout all the points in the domain. So that's why the right hand limit is also 2. Okay. So let me take slightly trickier example. What about your greatest integer function? Okay, so f of x is, so I'm taking the greatest integer function. So what is the value of f of 0.5?
1.
Sorry,
1.
no, this
1.
is why this is 1. What is the definition of greatest integer function?
Greatest integer greater than the number
Greatest,
given.
no, great, the value, basically the greatest integer function is the greatest integer which is less
So 0.
than
0.
x.
So it will be 0.
Yeah, so this is 0. Okay.
What is
uh,
that, sir? Why it is 0?
so by definition actually it's, so what is f of, so f of 0 is basically the greatest f of 0.5 is basically the greatest integer which is less than 0.5.
Okay, sir.
So this is 0, right? The greatest integer which is less than equal to 0.5. Okay, so basically it's basically the greatest integer which is integer greatest integer which is uh, less than equal to x. Okay, so the greatest integer which is less than equal to 0.5 is 0. Okay, then what about f of 1?
1.
1. Okay, so so okay, so let me try to so let me draw the graph of this. So this is 0. Okay, you can write it as 0 comma 0, but I'm just simply I'm writing the values of x. Okay, so so let's say this is 1, this is 2. So as you can see in this interval, okay, so in this interval 0 to 1, okay, if x is in bit is less than 1 and greater than equal to 0, then what will be the value of f of x?
0.
It's 0, right? So in this interval the value of the function is, so in this interval the value of the function is this, okay, 0, right? Now, so now at, if x equal to 1, if x equal to 1, then the value of the function is 1, right?
Yes, sir.
So in this interval, if you check this interval, then the value of the function is basically 1, excluding this point 2, because at 2 the value of the function is 2. So at 2 the value of the function is somewhere here. Okay, so at 2 this is 2, f of 2. So f of 2 is basically 2. Okay. And this point is 1 f of 1. So f of 1 is basically 1, right? So this is how the graph of this function looks like in the interval uh, 0 comma 2, right? This is how, if you draw, this is how it will look like. Okay, so so what I want to do now, I want to compute the left hand limit and right hand limit of this function at a equal to 1. Okay, so what I want to do now, I want to the compute the left hand limit and right hand limit of this function at x equal to 1. Okay, so first try to compute the left hand limit of this function at x equal to 1. Any guess?
So it is 1 plus, na, or 1 minus?
Sorry, it's 1 minus. Yeah.
0.
Sorry?
0. It is 0.
0. Yeah. Why it is 0?
Because as you approach from the left hand side, whichever value you take between 0 and 1, the value of the function will be 0. And uh, we are saying that any value you take close to 1, less than 1,
Yes.
it is always 0.
Exactly. Yeah. So you are correct. So so as you can see, what actually we are doing here, we are computing the left hand limit. So basically what I'm trying to do, I'm trying to so I am trying to find when x approaches to 1, when x approaches to 1 from the left hand side, I want to know where my f of x approaches, right? So when I'll come to 1 from the left hand side, this is my 0, this is my 1. So if I'll come to 1 from the left hand side, if I take any number in between 0 to 1, okay, so any number which is even, it doesn't matter how close it is, okay, it's until unless it's not equal to 1, okay, it doesn't matter how close it is, okay, it doesn't matter how close it is to 1, the value of f of x is always 0, right? It doesn't matter how close it is to 1, okay, the value of the function is always 0. So basically when I'm coming to 1 from the left hand side, the value of the function is always 0, right? That's why I can say that basically f of x is, it's not approaches to 0, it's basically 0, right? So that's why the limit of this function, left hand limit of this function is 0. Is it clear why the left hand limit of this function is 0? See, basically you are going to do the same thing for all the functions. Okay, so once you know how you are computing the left hand limit and right hand limit, even for a simple function, you can apply to all the function. Okay, you are not doing anything extra for some complicated function. You are doing the same thing. Okay. Is it clear, like how we are getting the left hand limit? The left hand limit is, so how you are computing that the left hand limit is 0?
Yes, sir. Clear.
Okay, so then it's, if you know how we are computing this left hand limit to be 0, then it's more or less clear like how you can compute the right hand limit, right? Right, so then what will be the value of the right hand limit?
1, sir.
1.
Yes, so the right hand limit is 1. Why? As you can see, so this is your 1, right? This is your 1. So when you are coming to this 1 from the right hand side, okay, can you, yeah, thanks. So when you are coming to this right hand 1 from the right hand side, if you take this point, as you can see at this point, the value of the function is 1, right? Even if you take this point, at this point, the value of the function is 1. It doesn't matter how you come close to 1, the value of the function is always 1, right? So it doesn't matter how you are close to 1 from the right hand side, the value of the function is always 1. So that's why the right hand limit is 1. So as you can see in this case, so in this case what we observe, the right hand limit. So in the case of constant function, what we observed, it's, so as you can see, it's this 0 is, so this is not special here. Okay, you can, instead of 0, you can compute left hand limit and right hand limit at any point. Okay, so so what we observed here, so in case of this constant function, the right hand limit and the left hand limit, they are always equal. Okay, so instead of 0, if you compute at 3, still here also, if you come from left hand side, the value of the function is always 2. If you come if you come from the right hand side, the value of the function is always 2. If you come from the left hand side, at that point also the value of the function is always 2. So it's nothing special about 0 here. Okay, it's true for all the points in the domain. Okay, so throughout all the points in the domain, the left hand limit and the right hand limit, they are basically same. Okay, but but here, as you can see, when we have computed the left hand limit and the right hand limit at 1, they are different. Okay, so for this greatest integer function, this left hand limit is not equal to right hand limit, right? So when I have so when I have this kind of scenario, in that case, I say that limit at x equal to 1 doesn't exist. Okay, so where the left hand limit and the right hand limit at a point, they are basically different, then you say that at that point limit doesn't exist. Okay, so let's say your left hand, if your left hand limit of a function is same as the right hand limit, let's say L, then you say limit exists at x equal to a, and you denote this as limit as x tends to a, f of x equal to L. This is how you don't denote the limit when your both left hand limit and right hand limit exist and they are equal. If the left hand limit and right hand limit, they are different, when the left hand limit is different from your right hand limit, then you say limit doesn't exist. Okay, so so in this case, as you can see, the limit of this function doesn't exist at 1. And similarly, can you see, like, similarly with the same argument, you can prove that the limit doesn't exist at 2, right?
Yes, sir.
Yeah, so similarly you can say that also the limit doesn't exist at 0. Okay, so this if you see this greatest integer function, so basically at all the, so if you take all the integer points, then at those points limit of this function doesn't exist. Okay. Is it clear?
Yes, sir.
Hello.
Yes, sir. Yes.
Okay, so let me open some uh, let's say this graph is visible, right, in Desmos?
Yes, sir.
Yeah. So so this is actually, as you can see, again, this is okay, so let me write down the function. So so this is the function of this, this is basically, it's a x minus 2 modulus by x minus 2 if x is not equal to 2, and it's 0 if x equal to 2, right? So basically so basically if x is less than 2, then what will be the value of this function?
Minus
If a,
1.
sorry,
Minus 1. Minus 1.
yes, it's minus 1, right? And if x is greater than 2, then the value of the function is
1. Plus 1.
plus 1. And at 2, the value of the function is 0. Okay, that is what, as you can see, at so at this point, at 2, the value of the function is 0. And if you are taking any other point, the value of the function is always 1. Right? This value is always 1. Okay.
So the limit doesn't exist, huh? At 2.
Why?
Friend of minus 1 and plus 1 at 2.
Yes. So the thing is,
Limit does not exist. Can we say?
yes. Basically, so yeah. So why actually limit doesn't exist? Because so the first thing is you have to compute the left hand limit, right?
Yes.
Yeah. So what is the left hand limit of this function at 2? At 2, what is the left hand limit of this function?
Minus 1.
Minus 1. Because when you are coming to 2, okay, so when you are coming to 2 from the left hand side, okay, so when you are coming to 2 from this left hand side, as you can see, the value of the function is basically minus 1. Okay, it's constant. It doesn't matter how close you are to 2 from the left hand side. Really doesn't matter, because the value of the function is constant for all the values which are less than 2. Okay, so it doesn't matter how close you are to 2 from the left hand side, the value of the function is always minus 1. Okay, it's always minus 1. Okay, so that's why the left hand limit of this function is minus 1. And similarly, if you are coming to 2 from this right hand side, okay, and you can see this value of the function is always 1. It doesn't matter how close you are to 2, the value of the function is constant. Okay, it's always 1. So as x approaches to 2 from the right hand side, f of x is, it's basically 1. It's basically 1. So that's why the left hand limit and right hand limit, they exist, but they are different at 2. Right? They both exist, but they are different. One is 1 and another one is minus 1. So that's why the limit doesn't exist. Okay. Any other function? Okay, this basically I have explained you. Okay, so yeah, just give me a minute. Okay, just give me a minute. Okay, I don't want this geometry. Let me open limit. My screen is visible, right?
No.
No, sir.
No, sir, it's not visible. Yes, now.
Okay, I don't know what actually I have opened. Well, I don't know. Maybe I have lost everything. Well, I don't know why actually it's not coming. Okay, so let me write it over here.
Now it's visible.
Okay, so okay, so let's say you have a function which is x square. Okay, so 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 what you want to do? You want to so this GeoAlgebra thing is visible, right?
Yes, sir.
Okay, fine. So what you want to do? Now you want to compute. Let's say the left-hand limit uh, of the function at this point, right? This at 0. Okay, so so this point A, this basically represent x, and this point basically represent your x comma f of x, right? So let me change the setting so that you can see the value. Okay, so this basically represent x. The first coordinate represent x, and the second coordinate represent your f of x. Okay, so so when you will come close to 0 from the right hand side, as you can see, when you are coming close to 0 from the right hand side, the value of the f of x approaches to where? When you are coming to 0 from the right hand side, where the value of f of x approaches?
0.
Exactly. Okay, when you are coming, so when you are coming close and close to 0, the value of the f of x basically approaches to 0. Okay, so that's why the right hand limit of this function, because here actually we are coming from the right hand side, right? So here we are coming from the right hand side. Okay, so that's why when we are coming from the right hand side, right hand side to 0, the value of the function approaches to 0. Okay, and similarly, if you come from the left hand side, let's say when you are coming to left hand side, okay, what happened? Just a minute. Yeah, so basically I want to show you from this left hand side, which is basically it's more or less clear that again it will go to 0. I don't know why. Okay, cool to do it. Okay, so yeah, so 0. So again, as you can see, when you are going to this 0 from the left hand side, and you can see that this function is basically the value of the function also approaches to 0 even from the left hand side. Okay, so here your both left hand limit and right hand limit, they are basically what? They are same,
Same.
and also they are equal to 0, right?
Yeah.
Yeah, so it's okay, so basically so it's more or less it's more than so this function is basically it's a nice function, so that's why this kind of behavior you can see this kind of behavior. Okay, so I'll take some function which is not uh, in some sense nice function. Okay, so let me take some piecewise function. Okay. Okay, so so as you can see, I have defined this function like this. Okay, so when x is less than 0, my value of the function is 2x plus 5, right? You can see here, right, how I defined this function.
Yes, sir. Yeah.
yeah. So yeah, so this is my function. If x is less than 0, the value of the function is 2x plus 5. And if the function, if x is in between 0, 2 and 3, that is greater than equal to 0 and less than 3, the value of the function is 3. Okay. And if x is greater than 3, the value of the function is
Minus x.
minus x. Okay. So this is how your graph will look like. Okay. So okay, this is how your graph will look like. Okay. So at 0, the value of the function is
Uh, 3.
3.
3. Okay. So
Three,
so
three.
0, at 0, the value of the function is 3. Okay.
It's also 5, right? Or not 5. Okay, less
No,
than.
no, no, because
Yeah,
okay,
yeah, it's
yeah.
less than.
And at 3, the value of the function is
Minus 3.
minus 3,
Minus
right?
3.
Yeah, at 3, the value of the function is minus 3. Okay. So so what basically I want to show you, so if so in this case we are trying to compute the limit, the left hand limit and the right hand limit of this function at 3, right? We want to compute the limit of the function at this point, this 3, right? So as you can see, so when I'm computing the left hand limit, okay, so when I'm computing the left hand limit, so when I'm going uh, so basically when I'm coming to 0, sorry, coming to 3 from the left hand side. So as you can see, the value of the function, okay, just a minute. So this when, as you can see, when this point D approaches to 3 comma 0, where this functional value approaches, it's basically 3, right?
Yeah.
So so when you are coming close to 3, the value of the function is always 3, right? So
Yes.
that's why the left hand limit is 3, right?
Yeah.
That's why the left hand limit is 3. So what about the right hand limit?
Minus 3.
Why?
Light.
Yeah. So yeah, your certainly your answer is correct. Okay. So let's say now I want.
Why don't we say left hand limit is nearing, we are not considering 2x plus 5 that.
Sorry,
We are not considering the 2x plus 5 function, right? For
it
left hand.
really doesn't matter. Okay. So basically, okay. So let me consider that function also. Okay. Let's say I'm considering that function also. So let me take the slider from,
And
let's
the
say,
left hand limit at 0, comma 0.
-2, right?
Yeah.
So so right, so this is my D and this is my functional value, but certainly as you can see it doesn't matter, because after certain stage you will cross that line, right? You will come to this thing, this line segment,
Okay.
because what actually we want to see, how f of x behaves when you are coming close to 3,
Okay. Okay.
right? Because if I'll take this point, even if I'll take some point in this negative x-axis, so eventually if I'll come close to 3, then eventually I have to jump from that line, and I have to come into this line segment.
Yes.
Okay.
Yes.
So when I'll come close to 3, then the value of the function is 3. Okay, from the left hand side. Okay, the value of the function is 3. Okay, so that's why the left hand limit is always 3. And what about the right hand limit? Okay, for the right hand limit, I have to change the slider. Let's say this is 5. This is 5, and this is minimum is
when it approaches 3, 0, even if it is left hand or right hand, it will become -3, right?
No. Why?
Less than 3 only, it is 3, right?
Yeah, so basically what actually you are doing, you are coming to 3 by using some number which are less than 3, right? You are not staying at 3, right? You are not staying at 3. You are coming to 3 by some number which are less than 3, and for left hand limit, and for the right hand limit you are coming near to 3, some number which are larger than 3. Okay, that is the difference. See, you are not, basically when you are checking the limit, actually the actual value of the function at that point is basically irrelevant. Okay, when you are computing limit, left hand limit and right hand limit, the value of the function at that particular point is completely, it's basically irrelevant when you are computing the limit. It doesn't matter what is the value of the function uh, uh, at that point. It's only, so what basically you are checking how the function behaves near to left hand side, to that left hand side of this 3, and the right hand side of that of 3. Okay, you are checking how the function behaves near to that point. Okay, you are not checking at particularly that point. Okay,
Thank you.
so okay, so this is, let me change, I don't know why. Okay,
Minimum 0 and maximum.
no, I'm computing now the right hand limit, right? So then I have to take numbers which are basically more than 3, right?
Yeah.
I have to take numbers which are more than 3. Now, if I'll come to this 3 by using some numbers which are larger than 3. Okay, so
Larger than.
yeah, so then basically I'm coming closer and closer to -3, right?
Yes.
Yeah, so basically I'm coming closer and closer to -3. Okay, so
Hmm.
that's why the right hand limit is
-3.
-3. Okay, so in for this function, as you can see, the left hand limit is 3, the right hand limit is -3, right? So both the limits, they're different. Okay,
At 3, 0, right?
at 3, yeah. So basically 30 is basically is yeah, so I cannot represent using 3, so that's why actually I'm using 3 comma 0, because I'm certainly drawing this function in um, in a plane. Okay, so it's basically it's 3. Okay, here x is 3. Yeah. So can you see again, using the same argument, you can say that at this point 0,
0. Yeah.
the limit is different, right? Because if you come from, if you'll if if you'll come to 0 from the right hand side, the limit value is
3.
3, and if you come to 0 from the left hand side, the limit value is
5.
5. Yeah, so because if you come, so you'll come closer to 5, not to 3. Okay, so that's why both the limit, they are different. So basically you can see that for this function you have only 2 points where the limit doesn't exist, right? That is 0, and that is another one is 3. You have only 2 points at which the limit of this function doesn't
Does not
exist.
exist.
Clear, right? So okay, so I don't know whether I have created uh, any other function. Yeah, so again similar kind of function. So you take this function. This is okay. So if x is less than 0, it's a linear function. If x is greater than 0, it's a quadratic function. Okay, because it's saying if x is less than 0, it's 1 plus x. Okay, and if x is greater than 0, greater than or equal to 0, it's x square. Okay, so that means at 0, the value of the function is 0, right? So again, if you compute, let's say the right hand limit of this function, if you compute the right hand limit of this function, so when you are computing the right hand limit of this function, as you can see, when you are coming, so this, when you are coming closer and closer to 0 from the right hand side, as you can see, the value of the function approaches to 0, right?
Correct. Yeah.
And similarly, as you can see also, so similarly, you can see, so when you are coming to 0 from the left hand side, as you can see, the value of the function approaches to
1.
1.
1, right? So the value of the function approaches to 1. Okay, so that's why the left hand limit and right hand limit, they're different. For one side you are getting 0 and another side you are getting 1. So that's why the limit doesn't exist. So you can clearly say 0 is the only point where the limit of this function doesn't exist.
So at -1, we say limit exists.
Yes, -1 its limit exists, because see it's -1. So as you can see, for -1, okay, so when you are coming to -1 from the left hand side, from the right hand side,
Yes, yes.
the value of the function is what? Approaches to
0.
0.
Minus.
And also if you see, when you are coming to -1 from the left hand side, the value of the function approaches to
0.
0. Okay, so that's why, so for -1, both left hand limit and right hand limit exist. So that's why both the limit exists. So basically, you can say, since both left hand limit and the right hand limit, they are same, so you can simply say that, okay, limit exists.
Sir, it will be 1 na? When we are approaching from right hand side at -1, at -1 we are approaching from right hand side, it will be 1 na?
No, well, see,
Zero.
when you are coming to -1 from the right hand side, okay, from the right hand, what will be the value of f of x?
Yeah. It will be 1. Oh, sorry, 1 plus x. 0. Yes, it's correct. 0.
0,
Sir.
0, 0. Don't, okay, so
1
yeah,
plus x.
simply
Yes,
you
got it.
see
Yeah.
see this point. Okay, see this point. It's basically, you can see, when you are coming closer to -1, then basically the value of the function is 0. Okay. Yeah, so basically you are coming to 0. And similarly, when you are coming from the left hand side also, the value of the function approaches to 0.
You got it. Sorry, sir.
Yeah, it's fine. So okay, so yeah, so as you can see, so this function, the only 0 is the only point where the limit doesn't exist. Clear, right?
Yes, yes. Clear.
Okay.
So,
And
when do we say continuous? The
yeah,
term,
I'll come to that. Okay, so
this is the definition of limit.
yeah, limit. So once you know, basically, once you know the value of the, how you can compute limit, then checking continuity comes free. Okay, you don't have to check much. Okay,
Right.
you just need to find the limit, and you need to check whether that limiting value is, whether it's equal to f of 1 or not. Okay, sorry, not f of 1, f of a or not. Okay, so let me do it, write it here. So the limit part is clear, right? how actually we are computing
sir.
limit. If you want, like I can, maybe I have time, I can show you some trigonometry function, because see, trigonometry function, it's actually finding limit is actually easy, because they are all continuous functions. So so okay, so one thing I want to say, like, so you must have seen some properties of limit in multivariable function. So that basically it's coming from your single variable properties. So all the properties what basically you have seen in multivariable, that is basically coming from your single variable. That is limit. Limit is additive. Okay, so limit of the product is basically product of the limits. Okay, and you can take the quotient of the limits. Okay, quickly let me write. So it's basically saying, if this, and so you have two function, f of x and g of x, and you know the limit of both the function at a, then actually you can get the limit of the sum of the function at a. So in other words, limit x tends to a, f of x plus g of x is,
M plus n.
yeah, so basically limit of f of x and limit of g of x, which is m plus n. So it's basically saying, if limit exists, so you have to understand, if limit exists, then you can use this. Okay, if you don't know the limit, then certainly you cannot use it. Okay, so so if the limit exists, then actually you can use the additive property. Okay, and similarly, instead of plus, you can use minus. And same thing for product.
Sir, does it mean that before writing these expressions, we have to find the limit at that point? The condition, what we are saying, that if limit exists, right? So before rearranging two functions, we have to ensure that limit exists at that point, right?
Yes. Basically, so see, suppose you want to find the limit of x tends to 0. Let's say x plus a. Okay. So the thing is, then you can say this is nothing but x x. So you know this is 0, this is 0, because you know this limit exists.
Because we know, right?
Yes, you know this limit exists. Okay.
Okay.
But for example, let's say,
No,
okay,
if let us talk. Say if there is some complicated,
yeah,
expression.
not forget about complicated. Even let's say this function, okay, 1 by x. Okay. If you take 1 by x, what is the graph of this function?
That to opposite side, that curvy line.
So
Yes. And from bottom also.
and right, this is how the graph of 1 by x
Yes.
looks like, right? So as you can see, this if you come close to 0 from the right hand side, where f of x approaches,
Undefined.
not,
Infinity.
it's not undefined, it's basically it's going towards infinity, right?
Infinity. Yes.
Yeah, since you are going towards positive, like this positive infinity, that's why your right hand limit doesn't exist, because it's not a, this plus infinity is not a real number, right? So you must have some real number to say that this right hand limit exists. Going towards plus infinity. So the right hand limit doesn't exist. Okay. So similarly, you can say that your left hand limit also doesn't exist. Okay, when you are going towards 0 from the right hand side. So when you are going towards 0 from the left hand side, as you can see, the value of the function
Minus infinity.
goes towards minus infinity. Okay, so here, so basically here right hand limit doesn't exist, left hand limit doesn't exist, right?
Yes, yes.
So basically the limit doesn't exist, right?
Even if they exist, if they're not equal, we still say it does not exist.
Yeah. So in this case, that doesn't exist. So left hand limit and right hand limit, they simply doesn't exist. So then also you say the limit doesn't exist. Okay. So because you need equality, both right hand limit and left hand limit should equal. So in this case, certainly it's not true. They are not equal. Okay. So the limit doesn't exist. So if I take, say, 1 by x minus 1 by x, right? So this certainly is not true. I cannot apply this rule, right? I cannot apply this rule.
Correct, because it becomes 0. Right?
This side is 0,
Yes.
but this is doesn't exist. This limit doesn't exist. I can only apply this rule once I know, okay, this limit exists and this limit exists, then I can apply this rule. So that is what I have written in the very beginning, that if the limit exists, then you can take the sum of individual limit. Okay, that is really important. Okay, if once you make sure that, okay, this limit exists and this limit exists, then I can take the sum. Okay. So you need this condition. Okay. So as you can see, you cannot take the individual limits because both of them doesn't exist. So but in this case, you are getting basically a zero function. So the left hand side has a limit, but the right hand side has no meaning also, because both the limit doesn't exist. So okay, so and similarly, if I'll put some extra condition that my number n is a non-zero number, so this n is non-zero, then I can talk about the quotient. Okay. If my number is non-zero, then I can talk about the quotient. So this is nothing but m by. Okay. So these are the properties of limits, and even the same thing goes for continuity and differentiability. Okay. Okay. So so next, let me define what do we mean by continuity. Okay. So so a function f is continuous at a if the limit of f at this point a exists. So if the limit exists, and this limit is nothing but precisely this limit, whatever this, so we'll get some L, right? This L is nothing but f of a. Okay, so this limit is nothing but f of a. Whatever limit you are getting, if that is precisely f of a, then you say that the function is continuous at. Is it clear?
Here I get a meaning that if there is a limit, then it is continuous. Is it correct? Or
No. Actually, that is slightly what I can say. So if there is a limit, then you can make this function to be continuous by some, that is basically called removal continuity. But for example, you define this function. Let's say I'm defining this function, right? So this is 1 if x is 0. This is -1 otherwise.
Okay.
So basically at 0 this is 1, right?
Yeah.
This is 0, and in other places
This is -1.
-1, right? So what is left hand limit?
Left hand limit will be
-1.
left hand limit at what point? At 0.
Sorry, 0. Yeah, left hand limit at 0.
It will be -1.
-1, right? So the left hand limit is -1. Then similarly, what is the right hand limit?
-1.
-1, right?
Yes.
So the limit exists, right?
Yeah, but f of 0 is 1.
But f of 0 is 1, right? But this, we have a limit. We have some L. Okay, we have some L for this function. This limit
Sir,
at
it will be -1, 0 plus -1.
yeah, sorry. So both the limits same, left hand limit and right hand limit, they are same. So we have some L, but the problem is in the definition of continuity, it says that this L should be equals to f of a. Okay, but whatever example I have taken, in this case, L is not equal to f of 0. Okay, so that's why this function is not continuous.
Okay.
So so that's why this,
if a function is continuous, then it has got limits.
yes, yeah, because that is what we need in the definition of continuity, right? When I can say this function is continuous at a, if I have a limit at a, right? Apart from that, I need one more extra condition. So apart from that, I need one more extra condition, that this limiting value has to be f of a. Okay, it cannot be some any random L. It has to be f of a. So okay, so let me take some example.
So, sir, for continuity, then at A, so right hand limit at A, left hand limit at A, and the value of FA. The three things must be equal, right?
Yeah, that is so when I'm saying that limit f of is f of a, so this is for this thing makes sense when I have left hand limit is same as the right hand limit. Okay. This notation, this particular notation makes sense when I have both left hand limit and right hand limit, they are equal.
Yes, sir.
So yeah, so for continuity, you need the left hand limit and right hand limit, and this
The value of function.
yeah, they have to be same as the value of the function. So as I said, once you know how to how to compute the limit, then continuity basically comes free. Okay, you simply you compute the limit, and once you compute the limit, and just you need to verify whether that limiting value equals to f of a or not. Okay, so for example, let me take okay, so here actually it's more or less clear, right? So
Yes, sir. This example is clear.
okay, so this is some different thing.
Here at -1, we say it is
continuous.
continuous.
Yeah. So basically, uh, so when when you are coming to -1 from the left hand side and right hand side. So when you are coming to -1 from the left hand side, you are getting the limit as
0.
1. Oh, sorry, 0. Correct. And also when you are coming to -1 from the left hand side, you are also getting 0.
0.
And as you can see, even the value of the function at -1 is also
0.
0. So in this case, you basically limit and the function value, they coincide. Okay. So since they coincide, your function is continuous.
So in single variable, there are only two sides, left and right. We have to.
Yes, that's why computing limit in single variable is easy. Oh, so because you just need to check from two sides. You see how the function behaves when you are coming from the left hand side, and you check how the function behaves when you are coming from the right hand side. But in the case of multivariable calculus, it's pretty difficult. Okay, because then you cannot uh, check for all the possible sites. Okay, because you have infinitely many. So okay, so yeah, so let me go back. Okay, so I want to take few examples. So any specific example you want me to discuss for continuity?
So take one rational function like x square minus 4 by x minus 2.
Sorry,
X square minus 4 by x minus 2.
x minus 2. So where you want to, so first of all, what is the domain of this function?
All real number except 2.
Yeah, so you want to give some value at 2.
At, at x equal to 2, we want to calculate.
Sorry.
Okay, so at x not equal to 2.
See, if 2 is not in the domain of the function, okay, then we cannot talk about limit.
So 2 is in the domain now because
No,
it will
he
cancel
defined
out.
this function.
X minus 2.
No,
X
at
minus
2
2
this.
will cancel out.
No, that you cannot cancel. See, you can cancel only when both the numbers are non-zero. At 2, both of them are 0, so you cannot cancel. Okay. So when you are putting 2, this is 0 and this is 0, so you cannot cancel. Okay.
So we can define x at x equal to 2 as 0.
Exactly. So see, the thing is, as you can see, so you are checking the value of the function at that point. Okay. So if if 2 is if 2 is not in the domain of f, that means f of 2 has no meaning, because if 2 is not in the domain, f of 2 has no meaning. Then we cannot talk about continuity, because we have to first compute the limit, and we have to check whether this limit is same as f of a or not. If this a is not in the domain of the function, then this f of a has no meaning. So first you have to make sure that whatever point you are trying to you are trying to check the continuity, that point has to be a member of the domain of the function. Okay, so for that you have to define.
But if we want to find continuous or limit at x equal to 0, then we can find.
Sure, because for there, because at 0 the function is yeah, basically it's defined, right?
Yeah.
But at 2 it's certainly it's undefined, because at 2, because you're both the denominator and numerator, they are basically 0, you cannot cancel it out.
Okay.
So let's define that at x equal to 2, the value of the function is, let's say, 0.
We can also define another value also, right?
Yes, fine.
Any
You can take, instead of 0, let's say you can take 1.
one.
So
Sir, then does it mean that we can calculate limit or continuity at any point except the point which do not belong to domain, right?
sorry, can you repeat?
We can check for existence of limit, and we can check for continuity at any point except the point which do not belong to domain. Is it a right statement?
No, it's not. It's not true for limit. Limit actually, for limit, even you can compute the limit of a function, even it is not in the domain of the function. Okay, because as I said, the value of the function at that point is completely irrelevant when you are computing the limit of the function.
Because it's just nearer to that. It's
Yeah,
not-
because we don't care what the value of the function is at that point. We just need to check what is the value of the function, how the function behaves when your x is very near to that point.
So
So
suppose you take suppose you take fx equal to 4 at x equal to 2. Suppose you take fx equal to 4 at x equal to 2.
yes, no issue. You
So
can.
will this function, can we say this function is continuous now?
We have to check. We have to check. Okay, so we have to check. So we have to first compute the left hand limit and the right hand limit. Okay, then only we can talk about
how to compute the left hand limit and right hand limit?
okay, so before that
Without graph.
I'll come to that, but before that let me show it in the graph. Certainly I'll do it completely algebraically. Okay, so what is that function? X square
X square minus 4 by x minus 2.
x minus 2, right?
Yeah, minus 2.
Just a minute.
Is this it is defined at x equal to 2?
No,
The graph
actually
is
it's actually it's there is okay, so
actually it will cancel. That's why.
no, it's at 2 it's not defined. Okay, so because I cannot zoom it so because it's basically you are
So this
checking
expression x square minus 4 can be written x minus 2 into x plus 2, right?
yeah, that
Therefore,
is
it will
true.
be finally x plus 2 only.
No, okay, so
I think there will be some bubble at x equal to 2.
sorry, just give me a minute.
X minus 2 will cancel, no? Up, numerator and denominator.
No, that is not correct. Just give me a minute. Wait.
Otherwise, how it will be linear?
No. It's not linear. It's not linear. Okay. So let me show it. Show this one in Desmos. Then you can actually see. X minus 2, right?
Yeah.
Well, actually there is some gap, okay, here. So here actually this gap is, it's really difficult for you to see. Okay, so just let me type. Okay, you can see if I type. So this is this is x. This is
f of
f
x.
of x. So let's say 2. Can you see? This
Undefined.
function is undefined. So the problem why this is happening. So this function is linear except 2, right? So if x is not 2, then this function is basically x plus 2, right?
Yes.
But the thing is, okay, you cannot zoom it so large that you can see, okay, at 2 this function is not defined. That is the problem. I cannot zoom it. Uh, Even doesn't matter how large I zoom it, still you cannot see that this function is not defined at 2. Okay, is it like you got my point, right?
Yes.
So
Yes,
yeah,
sir.
so it's not possible for you to see that at 2 it's actually not defined.
So
Okay,
this
Well,
limit
limit
exists, but it
exists at 2. Limit exists at 2, but it is not continuous at 2.
it's limit, yeah, basically limit exists at 2. Okay,
Not
but
continuous at 2.
no, it's basically, as you
Okay,
can
we can
see.
say that limit exists, sir, huh? At 2.
Yes, yes, limit actually exists. Let me do it formally. Okay, so okay, so you want to compute the left hand limit, right?
yes.
So you want to compute the left hand limit. So basically, what you want to see, you want to see when x approaches to 2 from the left hand side, right? See, so when you take a point which is close to 2, then certainly it's not equal to 2, right?
Yes, correct.
I'm taking number which are close to 2 but not equal to 2. Okay, so in that case this is not 0, right? So in that case I can cancel this out because my 2 is not x is not 2. So in that case I can write x minus 2 x plus 2 x minus 2, and since I'm taking a number which is very very close to 2 but it's not 2, that means my x minus 2 is not 0, right?
Yeah.
So in that case I can cancel this one and this one because both of them are non-zero. So
Okay.
basically what I'm doing, I'm taking x minus 2 2. So when I'm going closer and closer to 2, this x plus 2 is going closer and closer to
4.
4, right? So that's why this limit is 4. Correct?
Yeah.
Clear actually why this limit is 4? When I'm computing this left hand limit, why I can cancel this out? Because I'm taking number which are less than 2 and which are very close to 2, but certainly they are not equal, they are not equals to 2.
Sir,
Okay.
suppose x minus 2 would have been equal to 0, then we would not have been cancelling it, right?
No, then I cannot cancel it. Okay,
Okay.
that is why this function is not defined at 2. Okay, so when I'm taking 2, then basically my x is 2. I cannot cancel this out. So what basically we are doing, x minus 2, x minus plus 2 by x minus 2. So when I'm taking x to be 2, this is 0 and this is 0. Then I cannot cancel this out. I cannot cancel this out. Until
So, sir,
unless both
0
of
and
them.
0 cannot be cancelled, right?
Yes. Then yeah, basically then you will then yeah. So whole number system collapse. So and so that's why the left hand limit is 4, right? And similarly, if you compute the right hand limit, in that case also you will get 4. Okay, you can compute, right? You can see, right, why this right hand limit is also 4.
Yes, sir.
Yeah. So basically both left hand limit and right hand limit, they are 4. Now I have defined that this function value is also 4 at 2, right? The value of the function at 2 is 4, right?
So now it becomes continuous, huh?
So now this is continuous. The left hand limit is same as right hand limit, and it's same as f of 2. So that's why this function f is continuous at x equal to 2. But okay, in the beginning Mohan suggested that okay, instead of 4, if I define it like, let's say 1, then I'm in trouble. My limit exists, but this function is not continuous. Okay, but instead of 1, if I define like this, let's say 4, then my function is continuous. Okay, so
So suppose if this function is not defined at 2, suppose function is not defined at 2, can we talk about limit existing at 2?
yes. If the function is not defined, then we have computed, right? The both left hand limit and right hand limit, they're same,
So
and they are
limit, we
basically,
can say that limit exists at 2, even though the function is not defined at 2. 2 is
yes.
not in the domain of the function. Still, we can say that.
Yes. For limit, it really doesn't matter whether that point is in your domain or not. Okay. So
We will only say it is not continuous. That's all.
yes. It's thing is, yeah. Basically, we cannot talk about continuity because this function is not defined at 2. Okay. So since this function is not defined at 2, yeah, basically we
If
can.
left hand limit and right hand limit tends to infinity, both sides, then do we say limit exists?
No, because
It is infinite.
because first of all, when you are saying left hand limit, when basically you are saying that see, when I have two numbers, okay, then only I can compare whether they are equal or not, right? So when you are saying that my left hand limit is basically going towards infinity, then I'm done. I'm out of my real number system. Okay. This then I cannot compare. Okay, so if left hand limit and right hand limit both tends to infinity, then you say left hand limit doesn't exist. You say right hand limit doesn't exist, and you say limit doesn't exist. Okay.
Yes.
Okay, so any other function you want me to discuss for continuity, or shall I move to differentiability?
Sir, while calculating limit, we also found something term called indeterminate form. Professor had used such term. So what do they actually mean?
Indeterminate form you use for this L'Hopital rule. Okay.
0 by 0.
Okay, so that is basically differentiable. Okay. So that certainly that this limit comes, but for example, sin x by x. Okay, so when you are computing this limit, you can see that you cannot apply this method, right? You cannot apply this method. Whatever this fourth thing I have written here, this quotient rule. So
Correct, sir. Correct.
in the quotient rule, what I have mentioned, first I have to make sure that this n is
GX should
non.
not be 0. Yes,
This
GX should
n,
not be 0.
yes, the limit of gx should not be 0. That is, this n should not be 0. But in this case, I cannot do that, because in this case my g is basically x. So limit x tends to 0, x is 0. So I cannot apply this rule. I cannot do that. Okay, I cannot do that. So when I have this kind of or even some other condition is there, even if it is in some kind of infinity by infinity form. Okay. So in that case, I cannot apply this quotient rule. Okay. So since I cannot apply the quotient rule, I have, so that is basically this, you call it as indeterminate form. Okay, so this then you, instead of computing the limit of f of x by g of x, you compute the limit of f dash x by g dash x. Okay. So that is basically your L'Hopital rule.
Right. Indeterminate form, the limit exists.
That is basically your L'Hopital rule. Okay, so for that you need differentiability. Okay, see, I can only talk about f dash x when yeah. So basically when I know differentiability, right?
Okay, sir.
So certainly it's this differentiability will help you to compute the limit. Okay, but before that you have to know what is differentiation.
Okay, sir.
Okay, so that is the thing. That's why actually I'm planning to discuss
Okay, so
this.
we'll come back to this again, right?
Yes, yes,
Okay.
yes.
Sir, just to confirm again,
Hmm.
suppose a function is not defined. Suppose two is not in the domain of the function, but
Hmm.
we can still talk about limits at a particular point which is not in the domain of the function, like we did in the previous example. Two was not in the domain of that function, but still we talked about limits at that function.
Yes,
Limits.
yes, yes.
Okay.
Ajay, sorry, can you repeat? Like,
I only said this 2 was not in the domain of this function. Still, we
yes,
talked about limits existing at 2, limit existing at 2 for this function.
yes,
Although 2 was not in the domain of the function, still.
yes, we can actually we can see, as I said, like what actually you are doing when you are computing limit. You are checking how the function behaves, how the function behaves. So suppose this is your x equal to a, how the function behaves when you are coming close to a from the left hand side and when you are coming close to a from the right hand side. So basically we don't care what is the value of a in that point, right? We certainly we're ignoring that, right? When I'm computing the left hand limit and when I'm computing the right hand limit, we simply we're ignoring the value of the function, right? So to be more precise, we don't want this function to be defined at x equal to a. Okay, because we are checking in some points which are nearer to a from in say from the left hand side and as well as from the right hand side. We are
That's a
checking.
domain doesn't matter. That's what, right, sir?
For yeah, so basically it doesn't matter whether a is in the domain of a or not. Okay, if a is not inside the domain of a, still I can I can talk about the limit. Okay, but certainly it has to be defined. It has to be defined on the points which are nearer to it. Okay, but for example, let's say uh, I'm so this is my function. Okay, I know. So this is my function. Let's say my function is 0 if x is less than 0. This is so the domain of the function is what? What is the domain of the function?
x less than
Basically minus infinity to 0, right?
0. Yes.
So in this case I cannot talk about the limit of the function at x is equal to 2.
Yes.
I cannot talk about the limit of the function at x equal to 2 because
It is not defined
it's not defined some points even nearer to 2, right? Because my function is only defined
until 0.
0, but here I can talk about the limit of the function at 0. Okay, so here basically the limit is basically the left hand limit. Okay, so
Yes. Left
if
hand limit
when
is there, but
yes,
right hand
it's
limit is not.
right hand limit, I cannot talk about the right hand limit. I can, if you tell me whether what is the left hand limit of this function at 0, then I can give you the answer. Okay, but if you ask me what is the limit of this function at 2, it has no meaning because this function is not defined at 2 and also it's not defined at at points which are even closer to 2. Okay,
Nearer
Sir,
to.
so yeah.
sir,
So
uh,
even at 0, we say limit does not exist because there is no
Uh,
right hand limit.
okay, so they actually okay. So I'll suggest okay, don't go on these things. Actually, in some sense, actually, since there is no meaning of right hand limit, okay, here. So that's why you can say that by computing only just the left hand limit, you can say, okay, that is the limit. Okay, so
So, sir, this function will be continuous, right? At 0,
no, this function is not continuous.
not continuous.
It is not defined at 0.
It's not defined at 0. So since it is not, this function is undefined at 0, then we cannot talk about continuity. As I said, we can only talk about the left hand limit of the function at 0. Okay, that's all.
So
Even we
limit
cannot.
exists at 0. Limit
Okay,
exists
as
at
as
0.
I said, since we are talking about only left hand limit, so just talk about left hand limit. Since we don't know what is right hand limit, so it's better, I'll suggest try to avoid this thing. Okay, so as I said, when you have this kind of scenario, that is, we can only talk about the left hand limit. Okay,
So, sir,
so
sometimes in the exam it is asked regarding a curve, and
hmm,
that curve, there's the endpoints of the curve,
hmm.
and sometimes it can be asked whether the limit exists at the endpoint.
Certainly, we are not going to ask you in this course. Okay, so there certainly there is a concept of limit when only you can talk about the left hand limit. Okay, there is still a concept of limit when you can only talk about left hand limit. Okay, but certainly we are not going to ask you in this course. Okay, so I'll suggest you try to ignore such type of cases. You say, "Oh, okay, since I only uh, since I can only talk about left hand limit, that is my left hand limit. Don't go to what will be the limit and all these things." Okay.
Okay.
And again, whatever, like, see, the thing is, what actually basically whatever we are doing here, we are doing vaguely. Okay, so actually still now I didn't give you the precise definition of limit. Okay, as you can see, I never defined what is limit. Okay, I'm simply, as x is close to a, this close has no meaning. Okay, until unless we are doing it geometrically. Okay, so I have to define what is algebraically, this close has no meaning. Okay. So again, whatever I'm doing, it's more or less vaguely. Okay, I'm not doing all the things formally. There is a definition of limit. Okay, which is slightly complicated.
Okay.
So same thing goes with continuity, and same thing goes with your sequences. Okay, so you must have studied, like, if an converges to a, this has some formal definition. Okay, so so I guess I'm done with limit. So again, one more thing I just want to say, that is basically sandwich lemma, which is it's in some sense is quite crucial when you are proving some result on limits, or maybe you know. Okay, so before that, let me give the statement. Sandwich lemma. Oh. So what it basically says, so suppose I know that limit of f of x as x tends to a is L, and I know limit as x tends to a g of x is L, and I have some other function which is h of x, right? I have some other function h of x which satisfy this condition, that h of x is less than g of x and is greater than f of x. Okay. Then it's saying that limit of
It is at a point x tends to a, right?
is L. Okay. So basically how we are getting, so if you take the limit here, So then basically this limit as x tends to a f of x so we know this limit, right? We know this is L and we know this is L, and we have something which is basically in between two numbers which are same, right? Then this has to be L. Okay. So this is in more or less this is very useful to compute limits of maybe some kind of function. Let's say, okay, let me take some example. So any example, you know how to apply sandwich lemma? Let's say x square sine square x. How you can compute the limit? So okay, even you can do it by the product rule here. So if you want to compute the limit of this function as x tends to 0, okay, how you can compute? So one way to compute this function is basically uh, see x square is always greater than 0 and sine square x is always greater than 0. Okay, so that means x square sine square x is always greater than 0, right?
Yes.
And you know sine square x is always less than equal to 1.
Right.
That means x square by sine square x is always less than x square. So if you take the limit, this limit is 0 as x tends to 0. This limit is 0 as x tends to 0. That's why this limit is also 0 as x tends to 0, right?
So the two separate functions are x square and sine square x. And these are the two separate fx and
No,
gx.
this is my f of x.
Now, according to the theorem, this is h of x. And
Acha, this is h of x, and my
f of x will be x square and g of x will be sine square x.
no, f of x is 0.
Okay.
F of x is 0. G of x is x square. Okay. So this is actually it's not in my opinion this is not a useful example. Okay, this is not good idea to apply sandwich theorem in this example. You cannot apply the product rule. Okay, so let me think about one more example. So I want to do some kind of quotient thing. Okay, so so let's say I want to find out the limit of cos square x divided by uh, e power x as x tends to infinity. right? I want to compute as x tends to infinity the limit of this function. Now can one of you tell me how I can compute this using sandwich principle?
0 is
Any
less
idea?
than cos square x. 0 is less than cos square x is less than 1.
Cos square
Divide
x
throughout is less than 1.
1, correct,
And divide throughout by e raised to x.
divided by e power x. So this is basically 0 less than cos square x e power x e power x. And if you take the limit as x tends to infinity, 0, what is the this limit as x tends to infinity? 1 by e power x.
1.
I'm talking about this limit.
Infinity, okay.
Infinity.
0.
0. Why? Because if you draw the graph of e power x, what is not e power x? E power minus x. What is the graph of e power minus x?
It's like that. So,
It's not exactly this. Probably I have made some mistake.
That's to cross y-axis.
Sorry.
That's to cross y-axis.
Yes. It has to cross y-axis. So 0 at 0,
1.
it's 1. Mm, then if it is it's small. Okay, e power x is basically it's a bounded function. Okay, so then probably it will go like this. Okay, so as you can see, as x tends to infinity, when when x is large, then basically as you can see this e power x going towards e power minus x going towards 0, right?
Yeah. Yes.
So that's why this limit is 0. Okay, so now since this side is 0, this side 0, that's why this side is 0. So
So,
so this,
sir, can I ask one question?
yes.
So, sir, in this sandwich lemma, how can we decide what will be the fx and what will be the gx?
That is actually there is no proper way, there is no algorithm through which you can decide that. Okay, that actually you have to choose
Based on
carefully.
experience.
Exactly, yeah. So
Okay.
you have to choose carefully. Okay, so if you do lot of problems, then probably it will be slightly easier for you to choose function. There is no such algorithm like how I can uh, take this function. Okay.
Okay.
Okay. So okay. So okay.
Differentiate.
Yeah. Okay. So let me start differentiation. I'll try to finish this today. So okay. So again, the thing is, the whole thing basically once you know how to compute limit, then more or less everything comes free. So so first thing is, okay, so definition. So so I have a function f is differentiable at a if limit h tends to 0, and if this limit exists and we have some value L, then you say
Sir, it
that
will be h tends to a or h tends to 0. Limit
h
h
tends to
to
0.
Okay.
You can actually, you can make it A, but then you have to slightly modify this one. Okay. So then you say that f dash A exists and it's equal to A. Okay. So, so basically, okay. So let me tell you what basically it's this thing is giving. Okay. So okay. So let's say I have a graph like this. Right? So this is my A. This is my A plus H, right?
Yes.
And what is this? This one is
F of A.
A f of A. And okay, so and what is this one?
A plus
This
A.
one is A plus H f of A plus H. Sorry. So okay, so whatever I have written here, forget about this limit now. Whatever I have written here. What is the meaning of this thing? If you try to interpret this one in terms of these points, what is the meaning of this expression?
Which is to
This is some ratio of change in value.
adjacent by opposite side.
The rate of change actually.
It's not rate of change. Forget about rate of change. All these things.
Adjacent
Okay.
side by opposite side.
So basically, if you draw a line
Hmm.
connecting these 2 points,
Hmm.
what you are saying that it's basically I'm
Gradient, sir. Actually, the
so
slope.
Opposite side by adjacent side, right? This one.
yes. So basically, this whatever this thing is here,
It is
this
tan theta.
yeah, tan theta. Okay, so my thing is okay, whatever you're saying, but what actually I'm saying, if you draw a line,
Hmm.
okay, containing join which passes through these 2 points, this is precisely the slope of that line, right?
Slope. Tan theta slope.
Right, this is how you define slope, right?
Correct. Yeah.
Now okay, now so this particular thing has this particular expression will give you the slope of this line, right?
Correct.
Now you come to this thing as limit extends to 0. So instead of that, again, so what do you mean by limits? So when so when h approaches to 0, this a plus h basically approaches to
A plus A.
a, right?
Yeah.
So again, if you come to some point which is even more closer to a, then you are taking some other line, right? You are taking another line. Okay. So basically, what basically it's giving. So when you come closer to A, so if you take the limit of this thing, so basically what it will, so it will give you basically the slope of this line, right?
Correct.
See, if I take even some other point which is even more closer to A, so again if I take the limit of these lines, then basically I will get the tangent of the function at point A, right?
Correct.
So basically what I am doing here, I am taking the limit of the slope of the lines which converges to the tangent, right?
Correct.
So so this basically this whatever I have written here, this thing, if this exists, this basically gives you the slope of the tangent of that line at that point. Okay, so let me uh, move this. So basically what I'm trying to say, I have a function, this is my A, this is my A plus S. First I am taking a line, this line. Okay, this will give me something. Then this is A plus S. Then I am taking some point which is even more close to A, because that is what we mean by H tends to 0. We are coming to A. Okay, so again you come to some point which is even more closer to A. Then I will get some other line. Okay, so basically I'm taking lot of lines. Okay,
Exactly.
so I'm checking where all this line converges. So eventually if that limit exists, you can see that this line basically converges to
The tangent.
the tangent. Okay.
The
This,
slopes are different for different lines, right?
yeah, different line. See, sequence, the terms of a sequence, they are different, but eventually you can see that eventually they are converging to some point, right? So
Yes.
this is basically happening. You have bunch of lines, and in the end you are checking where it converges. Okay, so this whatever I have written here, this basically tells you the slope of that line. Okay.
Okay.
Obviously if obviously it has to be, certainly if it doesn't exist, then basically we say that, then basically it tells that you don't have a unique tangent line at that point. Okay, so you can have multiple tangent line. Okay, so it's clear, right? Like what is actually this
But
whatever I
tangent line is only unique na, at that point.
that is actually if this limit exists. Okay, then actually it's unique, otherwise it's not unique.
Okay.
Okay, so in that, when the tangent line is not unique, we say that the tangent line at that point doesn't exist. Okay, so when the tangent line is not unique. Okay, so for example, if you take this function, see, for this function, this is also a tangent line, right?
Right.
Yes.
This is also a tangent line.
At that point, at 0, 0.
At 0, 0. Okay. This is
Correct.
also a tangent line. This is also a tangent line. So in this case, you have multiple tangent line. That's why you say that tangent at 0. So basically, you say for this function, we don't have any tangent at 0.
So just a small doubt. So are
Hmm.
slopes same for all these three lines? Like we discussed now, the three tangent lines are there. So are slopes same?
No, they are not same, because okay. So let me take this function and let me find the derivative. So this is mod of this. Basically, this is the graph of this function, right?
Oh.
This is basically mod of x. Okay, whatever graph I have taken. So I want to find the derivative of this function at 0. What is the derivative of this function at 0? So this basically, as h tends to 0, f of 0 plus h minus
F of
0
0.
by h. So f of, what is f of 0? It's 0, right?
Yeah.
So what is this limit?
This is, we cannot say
Left
0.
hand limit is -1 and right hand limit
We have
is
already computed limit of this function. This is basically what? This is same as computing limit of this function at x equal to 0, right?
Yeah.
So we have already computed that left hand limit is -1, right hand limit is 1. So that's why this limit
does not.
doesn't exist. So that's why this, if you, so since this limit doesn't exist, that's why you say this function is not differentiable at x equal to 0. Okay, since this function is not differentiable, that's why you can
So
see
just a small request. Could you elaborate on this? If I approach from left hand side, then what will be value?
uh, that is -1.
This one.
Because h and h will cancel.
Yes, yes.
-1.
We have already computed, right, this for, let's say, this function, this
X minus 2.
what is the graph of this function? Mod x by x. What is the graph of this function if x is less than 0? This is -1, right?
Yeah.
And if x is positive, this is +1. So the left hand limit is -1, the right hand limit is 1. Okay, so that's why, as you can see, this function is not differentiable at x equal to 0. Okay, and since actually, basically, since this is not differentiable, that's why actually we can have multiple tangents.
By this graph, if we go when before my 0 in the minus side, it is approaching 0, right? F of
Sorry, which one you are talking now?
by this graph, the
This one.
the graph, no? Not for this.
So this
For,
is fine. This limit doesn't exist, fine, right?
yeah, yes, yes.
Okay, so now let's go to the graph. Okay, now you take the graph. Yeah. Yes. What is the issue now?
You said it is -1, right?
Which one? -1, I said.
For this one, this is not. Sorry, this is not mod x by x, right?
This one.
This is only mod x graph.
This is only mod x graph.
Okay, understood.
Mod x by x graph is this one.
Yeah, straight. Yes.
So see the why actually the problem, why actually this function is not differentiable. See, if you take, so what actually we're computing here, limit h tends to 0, f of a plus s minus f of a by h, right? So here a is 0. So this point is my fix 0, 0. So I am coming from h equal to 0, right? So when I'm taking this line, okay, tangent of slope of this line, I'm getting what? 1, right?
Yeah.
even if I take some smaller edge, so even if I take some smaller edge, then also I'll get the same line, right?
Yes.
That slope of that line is 1, right?
Yes.
So when I'm coming from my right hand side, whatever lines I am getting, slope of all these lines are 1, right? But when I'm doing from the left hand side, whatever lines I am getting, slope of all these lines are
Minus 1.
minus 1. Okay, so basically I'm getting two different tangents. Okay, this is one tangent, this is another tangent. Okay, so that's why this function is not differentiable at 0. Okay, so we can say that this function is differentiable at a point if and only this function has a unique tangent at that. Because when I'm coming from the left hand side, I'm actually getting all whatever secant line I'm taking, all these lines they have slope 1, and when I'm coming from the when I'm coming from the right hand side, whatever secant line I'm taking, all of them have slope 1. When I'm coming from the left hand side, whatever line I'm taking, all of them have slope minus 1. Okay, so that is the difference. That's why this function is not differentiable. Yes.
Sir, is this the region? Just I'm trying to connect the dot. Is this the
Hmm.
region that any curve which is having a sharp point, we say that it is not a curve at all?
Not a
Like,
curve, not the function is not differentiable at that point.
no, while in school days we used to study, what is meant by curve. Then we used to study that whenever we draw a shape, right, without
Hmm.
lifting the pen, then that is called curve, right?
No, no,
But
no. Without lifting the pen, then that is a continuous thing. Okay, so see, okay, so there is okay. I don't know what. So what do you mean by curve? Okay, in more or less, uh, is curve. Okay, I agree that in the definition of curve, you need smoothness. Okay, so it has to be smooth. So so yeah, so you don't call this one as a curve.
no, because we had to lift our pen.
No, no, it's not lifting. See, lifting a pen is basically it's related to continuity.
Okay,
Okay,
okay.
so continuous means you can draw without lifting the your you cannot draw the function without lifting your pen. Okay,
Okay, so this is a curve. Right
this
now,
is this
whatever you
is
have
this
drawn, this is
is
a curve.
this is a continuous function. Okay, so
Yes, correct.
because I can draw it without lifting my pen.
But if it has a sharp
But
edge, say for example, if it has a sharp edge at any point, so
hmm,
that we can still call it as a curve. Like you draw a curve having a sharp edge.
actually that is okay. So you need differentiability. Okay, usually you don't call it as a curve. Okay, this is basically this is not a curve. Okay, because it has a sharp edge over here.
You this is not a function, right?
This is a function.
This is a function. Okay.
Yeah.
So, sir, at this the sharp point which we were talking about,
Hmm.
at this we can draw many tangents. That's why,
Yeah, basically at this point this function is not differentiable.
yes.
Okay.
So for a curve, it has to be differentiable at every point.
Yes, yes, that is how you define curve. Okay. In more or less that you call it as a smooth curve. Okay, so
Smooth curve. Okay.
yes.
Answer my second question is that as you said that limit doesn't exist, so it is not differentiable at this point.
Hmm.
So just couple of no, just 10-15 minutes back we discussed that limit and continuity. So
Hmm.
say for example, if my limit doesn't exist, then I should not check about continuity, and I can immediately say that it is not differentiable at this point, right?
Hmm. Hmm. Hmm.
But if limit exists, then definitely we have to check for continuity, and then we can confirm whether it is differentiable or not at a point,
After
right?
checking continuity, you have to check whether this function is differentiable or not. Yeah.
Okay, but if limit doesn't exist, then we can directly say that this is not differentiable, right?
Yes. Yes. Yes.
Okay.
See,
Sir,
if the
you have an example where if it is continuous and limit exists, but it is not differentiable.
that is I was precisely I'm taking this function. That is what I have done. This f of x equal to mod x. Whatever you said, it's true, but it's not differentiable at 0.
But in this case, limit also doesn't exist, no, sir?
differentiable implies continuity implies limit.
So mod of x limit is existing. It is continuous, but it is not differentiable.
Not differentiable. No, Ganga Prasad, what actually you are doing? You are taking a different function. See, when you are computing the differentiability, you are taking the quotient, right? You are not taking the same function, right? You are taking some different function. You are checking the quotient, right? I am saying limit of this one doesn't exist.
Okay.
I am not saying that. See, this is a different function from mod of x, right?
Correct.
This is my function, but this is another function, right? So when I'm computing differentiability, I'm coming back to some different function. When I'm taking the quotient, I'm getting a different function. I'm not with the
Okay.
same function.
So the limit of this function doesn't exist, right? Mod
Limit
x by
of this,
x.
since the limit of this function doesn't exist, that's why we say that this function, this f is not differentiable.
So, sir, can we say that this function represents the tangent actually at that point?
Which function?
This x mod x by x actually.
No, this function doesn't represent the tangent of that function.
Okay.
No. This is a different thing. This limit will give you the slope of that tangent. Tangent is basically, it's a line.
Yes.
It will come in the form of a function. Okay, this is something different. Okay.
This is the slope of the tangent.
Yeah. This what if I will get a limit. Certainly in this case I don't have a limit. If I will get some limit, then that limit, whatever limit I will get, it will give you the slope of that line. Okay, it's
Correct. So basically, sir, when we say slope, basically it's the slope of the tangent line, right?
yes, slope of the tangent. Okay. So yeah, so this is basically differentiability implies continuity, implies once you have function is continuous, then you have limit. Okay. So this is okay. So as you said, if you draw the graph, if we have some kind of sharp edge, then basically the function is not differentiable at x equal to at that point. For example, if you take x square, it's actually differentiable everywhere, because if you draw the graph, then basically it's smooth everywhere. Okay, and also you can compute the limit. Suppose I want to compute the limit of this function at some point a. Okay, how I'll compute? I want to find the derivative of this function at x equal to a. What is the definition? This is h tends to 0, f of a plus s minus f of a by h, right?
Yes.
So so this is nothing but this is a plus h square minus a square
By h.
Okay, so this is
H square
a
plus
square
2h minus a square.
So this one get cancelled.
H plus 2a. H plus 2a.
Yeah. So basically h plus 2a, right?
Yeah.
And as h tends to 0, I am getting
2a.
2a. So that's why the derivative of this function at a is 2a, right?
Sir, I may be mixing two things, but sometimes we also write the h tends to a. When do we write h tends to a? Sometimes we also write
Which one? Where you
like
write?
here we are writing h tends to 0.
Ah.
Sometimes we also write the h tends to a.
H tends to,
Or I may be mixing, sir. Don't get into this. I may be mixing some other concept. H
no,
tends
no,
to
no, no.
A.
Whatever you are saying is correct. But okay, so the thing is, there are multiple ways of writing the same thing. Okay,
Okay.
so okay, so basically, I guess you can write this basically same as limit uh, h tends let's say uh, x tends to uh, a. Mm, so, but basically, it's now uh, I have x equal to a plus s. Mm, then a is basically x plus s. So as a tends
F
to
of x
0,
minus
X
sorry,
minus
f of x
H.
minus f of x minus f of a.
f of
X
x,
minus f of a by x minus
f of x minus
f of a
a
by x
by
minus a. X
x
minus
minus, yeah, yeah, correct, yeah. So, so yeah, so you must have seen something like this. Okay, so basically
Sir,
you are
will it be x minus h? A equals to x minus h, or like
sorry,
A
uh,
equal to minus H, right?
you took
uh,
x equal to a plus h, and then a will be x minus h, right? Or,
it's I guess it's x minus a, no, it's fine, I guess. Yeah. So because what basically you are doing, you are taking the slope of this line, x, f of x, and a f of a, right?
okay,
Fine. This is the slope of this line, right?
No, no, no. What is above the rectangle box on the top side?
Hmm.
You have
yes,
written
sir,
A
where a
plus
equal to a
H.
plus h you have written, and then below it you have written a equal to x plus h. That will be x minus h, sir.
Which one you are saying? This
Above the
one.
box.
And above the box part that you have written, where you have written x equal to a plus h, and
Okay,
below
this
that,
one.
Ah,
yes, yes, yes.
No, then basically here you have to change this one. Okay, so basically if I will write here x minus a, okay, so then as you can see, uh, here
no,
the
you
value
X
of,
plus H you have put.
so then the value of a plus h will be different. Okay, so basically what I think what uh, he has done, he has written x is basically a minus x. Okay,
Okay,
so
okay,
whoever recommended me to write this one, so he actually, instead of x is equal to a plus h, he has taken x is equal to a minus h.
minus h. Okay.
Yeah, so
Oh,
that's why he is getting this one. So as I said, they are basically same. Okay,
okay,
so
okay.
instead of, even if instead of if you type write f of a minus, you can also take f of a minus f of x by a minus x. That also will give you the same thing. We are just multiplying minus 1 in both denominator and numerator. So basically what you are doing, the same thing, right? So basically
Correct.
what you are doing, so you are taking this x, f of x, and you have some point a
Yeah.
and f of a, and you are coming from a
Yeah,
to
good.
x, and similarly you are coming from the left hand side and as well as from the right hand side. Okay, so in more or less whatever you are doing here,
Okay, okay.
you are doing the same thing here. Okay,
Sir, in
because
this below calculation, we are not coming left side, right side. That is not there
which one?
in this calculation which you did 2A.
So the thing is, if you do, you will get the same thing. So I'm actually here when I'm computing this limit, I'm in actually I'm uh, ignoring that left hand limit and right hand limit. Okay, if
You
basically
don't
if
have
you, Yeah, if you compute the left hand limit and right hand limit, you will get 2. Okay. Okay. So since I have already discussed a lot about limit, okay, so that's why actually I'm not trying to compute to.
No, basically, when we differentiate, we don't have to do that. Left hand side and right
You
side.
should do that, but see, you know that this limit exists. Okay, so then why you will compute the limit
Therefore,
individually? Okay, so see, if you know,
Conceptually, we should do this.
yeah,
Conceptually, we should do
yeah.
that.
So you should see. I can only talk about limit when I have both left hand limit and right hand limit. Okay,
so
so
in that case, I have to consider x minus h, a minus h, and like that. From a minus h, I have to go to a.
yes, yes. So when you will compute, so in this case, when you will compute the left hand limit,
Mhm.
what is this? Limit s tends to 0 minus s plus 2. So,
Mhm.
so okay, so when you are coming to 0
Mhm.
from the left hand side,
Mhm.
what you will get? 0, right?
Yeah, yeah, 0. Yes,
So
yes.
this is 2a. So when you are coming to 0 from the left hand side, also you will get 2a, this
Mhm.
whatever is. So as I said again, so uh, I'm actually ignoring all these things. I'm not computing this left hand limit and right hand limit, since I know both left hand limit and right hand limit, they exist and they equal. That's why I simply wrote 2.
Okay. Okay.
Yeah, so okay, so I guess, okay, so that is what differentiability is. So okay, I guess I'll stop now. I'll try to arrange one more session, and I'll
Yes.
talk about differentiability a little more, and then I'll go to critical points. Okay. So I don't
Okay,
think
sir.
I'm.
Area under the curve, sir.
No, area under the curve is not needed for multivariable calculus. Okay, so uh,
Calculus 1 we have used in
no,
math,
so
sir.
so the thing is, okay. So thing is, there are lot of recording of live session, like solve with a session are there in YouTube. Okay, so you can go and watch. Okay, so but see, the point is, why actually I'm saying, we cannot uh, discuss whole 3 week things. Okay, so that is
Sir,
not okay.
in that case, at least release activity question and other practice questions, sir.
No, that we have already released.
No, sir. Those are not available in YouTube, na.
No, no,
Whatever you
no.
are saying, only no
Question,
recording
right?
says questions. Questions are not available, na, sir.
No, no, no. Questions are available in your portal.
Total it is there. Three
Yes,
weeks.
we have published it in the portal. Okay, so we have released all the
Mohan Raj, have you checked questions are there?
yes, yes, yes.
I think questions are there.
Okay,
Uh,
then let me check again because videos
no,
are there in our portal. That
not
revision of
no,
math
no, no.
one.
Okay, so actually, I guess Mohan himself actually posted this in discourse. Then after that, I remember we actually published on all these things in the portal. Okay, so as far as I remember, it's there. Okay,
No,
so
videos are available, sir. Videos I have also seen. I have gone through those videos,
okay,
but
you go
questions I
through it. No,
but
question
questions
is
I
there.
have
You
not
There
please.
seen.
are all questions also are there. Assignment questions are there.
Yeah.
And
So.
activity questions also, right?
Mhm.
Yes, yes. Activity
Yeah,
questions also.
let me check. Thank you. Thank you.
There is a
So
PDF.
Okay.
yeah. So the thing is, so basically, for this math too, I guess you need only this limit continuity. Okay. More or less, you need
Have one
slight.
more session at
Uh,
least.
sorry.
Have one more session. As you said, na, that you will have one more session.
Yeah,
Na?
yeah, we'll try to, because see, the problem is the time thing. Okay, we'll try to. Actually, I wanted to discuss this what these critical points. Okay, so in the next session, probably I will try to discuss only this differentiability and critical points. Okay.
Yes,
So
yes.
again, I'll try to recall few things from differentiability, and I'll try to show you something on GeoAlgebra, because I don't think I can do it now. Okay.
Any tentative schedule, sir? By when? Of course, we
Uh,
will have it after Sunday because on Sunday we have exam. So any
yeah,
tentative?
yeah, yes. Certainly, we'll do it. Okay, I'll talk to Subhajit. Then only I can tell you. Okay, because
Tentatively, when it will come? Do
uh,
you have any
will let you know. Like I am not sure when you have a session of other subjects. Okay, so that certainly I don't Okay, I have to discuss with.
We can keep it on Wednesday, sir. Generally, on Wednesday we don't have any sessions, sir. On Wednesday we don't have any sessions.
You really don't have any problem of taking session on Wednesday?
No, sir.
At the
We can
same
check
time,
with
right?
we can
Evening,
check with
7 to
other
9.
people also.
Yeah, 7 o'clock. It's fine. Yeah.
Yeah, 7 o'clock on Wednesday, sir.
Okay, fine. Yeah. Okay, then probably we'll continue from here. Okay. Okay.
Okay.
Okay, fine. Okay, thanks.
Thanks a lot, sir.
Yeah,
Thanks a
yeah,
lot.
thanks.
Thank you very much.
Yeah, thanks.
Okay, sir.